So right now we're going to do a thermal effects problem. A 60-foot rail, A36 steel, is cross-sectional area of 12.3 inches. The coldest day we'll see is minus 30 degrees Fahrenheit, and the hottest day is 110. If it is unrestrained, what is the change in length? If it is restrained, what is the stress developed? What is the force that must be resisted? Like most problems, all problems, we're going to first give the givens. Given, it's 60 foot, or I'm going to convert it right away to 720 inches. The area is 12.3 inches squared. The change in temperature is minus 30 minus 110 degrees is 140 degrees Fahrenheit. And we're going to leave it unitless just to understand whether it expands or contracts. This is the maximum movement. It's A36 steel. And A36 steel, we know, has a coefficient of thermal expansion of 6.5 times 10 to the minus 6th inches per inch per degree F. The modulus of elasticity of steel A36 is 29,000, and that is KSIs. What do we need to find? In the unrestrained case, the elongation, lambda. In the restrained case, we need to find the stress, F, and the load, P. So let's look at the unrestrained case. And here we have the formula. The elongation is a coefficient of thermal expansion times the length times the change in temperature. The coefficient of thermal expansion, 6.5 times 10 to minus 6. The length is 720 inches. And the change in temperature is 140 degrees F. Let's look at our units. Degrees F cancel out, inches per inch cancel out, and we're left for inches with what we want. And the answer is 0.66 inches. Let's check for reasonableness. We have a 60-foot rail. The temperature changes an awful lot. Is it going to move 5/8 of an inch? Yeah, probably move 5/8 of an inch. Sounds reasonable. Now look at the unrestrained case. Oh, pardon me, the restraint. 3, 2, 1, go. Now we're going to look at the restrained case. And here we have the stress formula, alpha delta T E. And the stress is equal to 6.5 times 10 to the minus 6 inches per inch per degree F. Delta T is 140 degrees F. And the modulus of elasticity is 29,000 KSI. Once again, we do units, inches per inch, degree F, and we're left with KSI. And we end up with a stress of 26.39 KSI. And we'll notice that on A36 steel, we know that it has a stress of 22,000 KSI maximum stress. And we're not going to worry about this for this problem, but it's actually overstressed. Then we're going to try to find the load. And we know that the stress is equal to the load divided by the area. The stress is found above, 2639 KSI. The load and the area is one of our givens. and we get a load of equal to 325 kips. We're going to look at reasonableness. 325,000 pounds, over 150 tons, which says that it's going to be quite difficult to restrain something against this movement. You're going to have some pretty strong supports. And the story is that either A, it's going to buckle, which is no good, or B, we're just going to create unrestrained, that we're going to put in some rollers or some sort of capacity to take up the 0.66 inches. But trying to restrain that type of number is quite difficult. So here you have a thermal effects problem.